So hopefully you've had enough time for your warm-up here. If you're still working, that's fine. Just go ahead and continue with it. With our warm-up, it's again just a little bit practicing that summer assignment algebra 1 material. Factoring, like I said, never goes away. We do it all throughout the year. So I'm just going to keep counting that for you. And then we've got standard form just to remind ourselves of that. So let's go ahead and factor these two guys. Remember, the very first thing we check for is the GCF. Do we have a GCF for number 1? Nope. Do we have a GCF for number 2? Nope. And actually, if you forget the GCF in the beginning, you can save yourself in the end. Just look at your final answer and check to see if you can pull out anything. If so, then pull it out and you're good to go. Just don't forget about that GCF. All right, so I need what multiplies to the outside, so negative 36, and add to the inside, so positive 16. What two numbers accomplish this?
18 and negative 2.
Good, 18 and negative 2. And if you're stuck trying to figure out the factors that work, you can't think of anything more, just go with 1 times what, 2 times what, 3 times what, 4 times what. Literally go through the list until you've exhausted all possibilities. If nothing works, then we call that correct. But we do have here 18 and negative 2. Because it's not a 1 in front, we have to actually do the regrouping. So I have 12x squared plus 18x minus 2x minus 3. And it doesn't matter if I wrote the 18 first or the 2 first. What property permits me to move those around?
Commutative property of addition.
Good, commutative property of addition. Awesome. Alright, so GCF, we've got 6x. Let's take it out, so we have 2x plus 3. Whenever there's that negative, take out that negative. And the negative one is all I can take out, so 2x plus 3. Insides match, that is exactly what I was hoping for. And left behind is 6x minus 1. Okay. And again, we have commutative property multiplication as well, so it doesn't matter if I've got this factor listed second. Questions with number 1? Do we agree with number 1? Always let me know if I make a mistake. I will not, I guarantee. Alright, so same idea over here. We said no GCF multiplies to negative 12 and adds to 1. Alright, what two numbers accomplish that? What multiplies to negative 12 and adds to positive 1? Evelyn, don't say that again. Good, positive 4, negative 3. So I have plus 4x minus 3x minus 1. GCF, GCF. So we've got 4x, 3x plus 1. Again, we can take out that negative 1. Insides match. Again, notice I'm working in an orderly fashion. It's okay if you go left, right, side, up and down. Just make sure you're working in a sequence and not just throwing stuff all over. Have that this equals this, which equals this, which equals this, and I've got my final answer. Alright, show me with thumbs how do we do on 1 and 2. Awesome. If you're a little iffy, hopefully it's a simple mistake. If you have questions, make sure you come see me. Make sure you do some factoring practice. We'll keep doing it throughout the year. Alright, number 3. Find the equation of a line in standard form that passes through these points. Alright, standard form. Who can tell me what the general format is for it? Correct.
AX plus BY equals C.
Very good. No, that's completely right. AX plus BY equals C. Okay, now I want you to turn and talk to your shoulder partner. I don't know if I mentioned your shoulder partners last time, so when I say shoulder partner, it's basically the desks are paired up, but we have some wonky lengths of desks. So these 2 rows will pair up, but my 2 ladies in the back will just turn and talk to each other. These 2 rows will pair up, but my 2 in the front will just turn and talk to each other. And we've got some wonkiness over here. So you'll pair up, and then you 2 will turn and talk to each other. So when I say shoulder partners, that's what I'm referring to. For this, you don't need to scoot your desks. I'll tell you if you need to actually scoot your desks. So I want you to turn and talk to your shoulder partner. And between the 2 of you, make sure you can recall the 2 restrictions on our formatting for standard form.
Slope.
All right, go bring it back up front. Who can name for me those two restrictions?
No negatives and no fractional digits.
Good. Now the no negatives applies only for A. We can't have negatives for the other things, but A has to stay positive. So we'll just put positives in there. And then, like you said, no fractions or negatives. Sorry, let me try again. No fractions or decimals. So no fractions or decimals. Now here they didn't give us in the starting equation. They only gave us 2 points. So it also doesn't specify what format you have to start in. So it's up to you if you want to do slope-intercept form or point-slope form. I personally like to do point-slope form, but you can do slope-intercept form, no big deal. But either way, we had to first find the slope. What did we get when we found our slope?
7 over -3.
Good, so we got -7/3. Is there anyone that needs me to go through the slope? You okay with that? All right, I'll go through it. So we've got, with our slope, it's y minus y. And again, it doesn't matter the order. Over x minus x. So I have a -7, this becomes plus positive. If you go the other order, you get a positive on top, negative at the bottom, so -7/3. All right, so I've got my slope. I'm going to go ahead with point slope form, just to show you some tricks of the trade again with that. Also because I have a point and a slope. It doesn't matter which point you use. I'm just going to use the first one. So y minus 3 equals my slope times x minus -1 would be plus 1. Always be careful with those negatives. All right. You can go ahead and distribute your -7/3 and then get rid of the fraction. Just like last class, I like to get rid of my fractions right away. So I'm going to go ahead and do that by multiplying by 3 on both sides. So over here on the left, I get 3y minus 9. Over here, my 3 reduces with my 3 in the denominator, so I'm just distributing my -7. And now I have no fractions. Again, if you want to distribute fraction and then get rid of it, that's perfect. All right, I just needed to get it in this format because I already don't have fractions or decimals. And conveniently, I add the 7x over, it's going to be positive. So I have positive 7x plus 3y. I need to add my 9 over -7 plus 9. Lost my equal sign there. Equals. And just again, double check that it does indeed go x first, then y equals our constant. Do you agree with that answer? Okay, any questions with number 3? Okay. So let's go take a look at our assignment sheet. Taking a look at what we're doing today. Today we are doing some actual geometry vocabulary, a lot of the basics for geometry. So a lot of vocabulary today, we're going to be learning lots of words. There are going to be words that you already are familiar with, but we're mathematically defining them. And then your homework tonight, you'll see we have lesson 2 homework and finish any vocabulary that you talk about. But next class is what I want to draw your attention to. So we do have our first quiz. That's going to be over our summer assignment in lesson 1. Lesson 1 was just doing more algebra review. So what we're learning today won't be on that quiz. We'll continue to talk about it more next class as well. So it's still important for you to do your homework, of course, but make sure you refresh memory the summer assignment material for that quiz. So the quiz will be over our algebra review with distance and midpoint formula. Have these memorized. You're not given any formulas on your quiz. So make sure you have those memorized. But we'll come in, I'll go over questions you have on your summer assignment or questions you have on your homework. We'll talk a little bit more about our material we're talking about today, and then you'll take your quiz. Okay, so We do have the longer weekend because we don't have school Friday. And we also don't have school Monday. So just keep that in mind to refresh your memory with algebra. Hopefully though, doing summer assignment and last class, it's gotten your brain back in order with it. Okay, questions with what's to come? Awesome. Okay, so then let's go and take a look at our homework. So our homework was that lesson 1. If I told you need to finish a problem, raise your hand so I can come around and give you your credit for that. But I'm going to go and bring up the answers. You check your answers, and we'll go over questions. Because next class we do have that very exciting quiz. So between now and next class, I want you to go on Blackboard and take a look at the key for the summer assignment. Okay, so I'm going to go and show you where it is on Blackboard. So you're greeted with this. You go to bar graph geometry. Woohoo! Alright. So again, everything is under course materials, and I have now made available to you the key for our summer assignment. So what I want you to do is go through, compare your answers with the answers here. I have all of the work for it. So if you messed up somewhere, you can go back and look at the work to see where you went wrong. Go back through, look, fix things so that you don't make those same mistakes on the summer assignment. Okay? And it has everything. Okay, so I want to talk about just a few kind of key areas. Our distance formula, some of us did 17, but then just decided we didn't want to do 18. You do need to know your distance formula for the quiz, so make sure you have that memorized. Go back here and make sure that you didn't mess up a sign somewhere. That was another common thing. -8 plus 1 gives us -7. That squared is cos of 49, not negative. Another thing was our cross products. So there are quite a few of us that didn't have work for 33 through 35. Now, I know 30 through 32, it's a pretty simple enough process that you might have been able to do in your head. But 33 through 35, where we're distributing and whatnot, you should definitely have some work to show for that. So make sure you are showing your work. Cross multiplying is something that we will be doing quite a bit this year, particularly when we get to similar triangles. We find that similar triangles are proportional, the sides are proportional, and so we use cross multiplying to solve these proportions. This is a proportion. So that is a tool we'll definitely be using come December time. Radical expressions here. So just a real quick reminder with this. And when we're adding or subtracting, so problems 40 through 42, in order to combine radicals, they have to have like radicals, which means they have to have the same radical on it. Now, as these were written, they all did not have the same radical. So you've got to first go through and simplify it. Okay. Now, for like number 40, when we simplify radicals, we get 8 and -2 root 7. Those do not have the same radical, so I cannot combine those together. That is not 6 root 7. We have to write it as 8 minus 2 root 7. Now, 41, when you simplify those, so it was root 242 plus root 200. Again, you have to simplify before you can add it together. This does not equal root 442. You have to first simplify it, and if they have the same radical as they do here, when they simplified, it was actually 11 root 2, 10 root 2. Notice they have the same radical, so yes, we can combine together. It's like saying 11x and 10x, same idea. They have to have like radicals. So we have 11 root 2's over here. Over there we've got 10 root 2's. In total we have 21 of them. And 21 what? 21 root 2's. Okay, so it has to have that like radical. If not, can't combine. I think that was it for here. Basically, when it is a radical, you want to simplify it before you do anything else. Same thing with our quotients for radicals. Really, all of them you'd want to simplify first, but especially 50 and 51. When we are rationalizing our denominator, Sure, you can multiply by root 45 on top and bottom in the beginning, but then you have to multiply 27 times 45. We don't have calculators. You only have so much time. You don't want to waste your brain power multiplying such big numbers when you have to break it down anyway. So always simplify those radicals first. When you do, it simplifies down much nicer. We have root 3 over root 5, and that's a lot easier to rationalize. Multiply by your root 5s on top and on the bottom, and those numbers are a lot smaller and easier to work with. Okay, so in general with radicals, you want to simplify those radicals first before you do anything with it. Okay. Good work catching the no solution and all real solutions to those last couple of systems. And then the final thing is talking about our factoring and quadratic formula here. Number 87 was indeed prime. You were not going crazy, it was indeed prime. You were tempted with 6 and 7, but that multiplied to positive 42. You're going to get the combination of negative 42 and positive 13. Overall, pretty good at the factoring. Some of us were a little shaky when we had the coefficients in front. You will most certainly see that again a million times this year, and you will definitely see that on your assessments. So make sure you know how to factor these coefficients in front. That's what we just did for our warm-up today. And then some of us grew a little faint apart here at the end and did not fully do our quadratic formula. Make sure you truly do know how to do that. It was not there just for fixing equals, it was there for a reason. I wanted you to do it for a reason. So make sure you look at that. Okay, so again, check your answers to the key on Blackboard, look at the work. If you can't figure out what you're doing wrong, you're still stuck, come see me for questions, or if you want to watch a video on Khan Academy or something. But just make sure you are ready for any of these topics on your summer assignment quiz. And for the whole year, I mean, literally every topic in here we use throughout the years. Make sure you're here. Okay, questions with summer assignments. Go. Awesome. I think we can finally start doing our geometry now. Let me make sure. We did homework. We did our warm-up. Summer assignment. Yes, we can do geometry. All right. So you'll notice your homework for tonight is lesson 2 homework, and then we probably won't get through every vocab word on here, so finish up any vocab that we did not get through on here. If you forgot to fill out the 2 forms on Blackboard, just make sure you get that done before next class. That's the textbook. You put in like what book number you got, and then just like student information form. Those are just Google forms. You don't have to print out anything. You just fill out the information and put it in, and I have access to it. Okay, so the very beginning of geometry can be pretty tedious because there's a ton of new vocabulary. We have to define a lot of terms. We have to go with the very technical mathematical definition before we can build upon that and do more with it. So today is one of those days where there's just a lot of information, a lot of new vocabulary, but we have to start off with that before we can talk about planes. We have to know what a plane is. Before we can talk about the intersection of a line and plane, we have to know what those items are. Before we can talk about linear pairs and their relationship to supplementary angles, we have to know what linear pairs are. So a lot of new vocabulary today. Now some of it, hopefully, you are familiar with. Some of it you've probably never heard of, such as few lines. So what I would like for you to do right now is just take about 30 seconds, and individually, I want you to look through both the front and the back side of this. And take a look at what is already filled in for you. Read that, see if you can try to make sense of it. But take note of which vocab things you are already familiar with, and perhaps which ones you have no idea, you've never heard of before. When I tell you to, I'll have you then turn to your shoulder partner and discuss kind of between the two of you, what do you know, what do you know? Okay, so right now just take 30 seconds, read through, and kind of take a look at the terms that are coming your way. Bless you. All right, and go ahead and talk with your shoulder partner. Remind them of your name. Say, hello, my name is so-and-so, and then discuss the terms.
I know. I know somebody
All right, let's go ahead and bring it back up front. So hopefully a good chunk of these terms are familiar to you. Now we will define some of them a little more specific than perhaps what you were taught in elementary school. But some of them are really just what you know from before. Now in high school geometry, we learned what's called Euclidean geometry after the mathematician Euclid, which means it's plane geometry, P-L-A-N-E. Talking about flat surfaces, not the airplanes, and not plane as in plain Jane. It doesn't, nothing exciting about it. So plane geometry and flat surfaces. If you ever decide to pursue mathematical fields, you might have to take non-Euclidean geometry, in which it's not flat surfaces, but curved surfaces as well. And that changes some of the structure of the geometry and the postulates and theorems we deal with. So we're dealing with flat surfaces. All right. So these first few terms, they are kind of our basic starting points, our building blocks. So these first ones we call undefined terms. And they're undefined in the sense that they're so basic that we don't have like a perfect definition for it. It's kind of a concept or an idea. So starting off with, we have, actually let's first talk about space. So space in geometry is a set of all points in 3 dimensions. So we're talking about pretty much anything everywhere. I could have a point right here. I could have a point on the board. I could have a line on the board, but I could also have a line just right here. So we're talking about pretty much everywhere. We're in 3 dimensions. So let's talk about what a point is. A point indicates a location and has no size. So although I can draw a point, we can, of course, zoom in even more and have a smaller point, smaller point, smaller point. So it tells us a location in space, but it has no size. So thus, it also has no measure. I can't measure that point, right? So I'm going to go make that note. It has no measure. And so again, I can talk about point A, right there, point C, down there. So it's just a location in space. Now let's string a bunch of points together, and we have a line. So a line is represented by a straight path, it's got to be straight, that extends in 2 opposite directions without end, so forever, never, never. It has no thickness. A line contains infinitely many points. That's not a very straight line. I'll use my line tool so it's a little better. All right. So a line is a straight path. We use arrows to indicate that it is a line, meaning it goes on forever and ever and ever. And because it goes on forever and ever and ever, can we measure a line? No, I cannot take a ruler out and measure it because it goes on forever. So it also has no measure. Now, let's suppose that we wanted to talk about this line specifically. All right, I will not change the color. That black and blue line there. We need to go ahead and put a couple points on it so we can refer to it by its name. So let's just go and slap on point A, slap on B. In order to refer to this line, I would go ahead and use the notation AB with a little line over top. Now we do need to have the arrows to indicate that it is a line versus a line segment. Okay. So when I say line AB, I'm talking about the line that contains points A and B. Now I could also say line BA. It's going to be the same line, right? It doesn't matter what order we put those points. Let's say that we had a third letter on there. C. You only need 2 letters to name a line. So you could call this line AC, line CA, line CB, BC, line AB, or BA. You don't have to use all 3 letters, just 2 of the letters to indicate which points is a line point. Now, let's break away from there and talk about a line segment. So a line segment is a part of a line that consists of 2 endpoints and all points between them. So basically, we cut off the ends, right? So if I were talking about line segment AB, our notation for that would be AB with a little line segment over top. Now, even though there's more than just segment AB happening in this picture, segment AB is just the segment from A to B. So I can use this picture to refer to segment AB. That it would just mean that when I say segment AB, I'm only talking about this here and not everything else on the outside. Now, because a line segment does have endpoints, it does have measure. So a line segment has measure. And we use different notation to represent that measure. This notation here, we don't put a circle around it when we write it, but this is the notation to mean the measure of line segment AB. Okay? We basically just remove the segment over top. But it's really important that you know this notation, because when you get to certain assessments, get to certain homework, it's going to say find BC. What this means is find the measure of BC, find the length of BC, find the distance of BC, which means I would want to know what is the length or the measure of the distance of just that chunk there. Okay. So this reads as the measure of AB. Some other key words to indicate that. So of course we have measure. We could also say length or distance. Because in geometry, a lot of times we have a picture we're working with. But of course we have that crossover to algebra, where sometimes we're talking about 2 points on a graph. So let's say I want to find BC. B is down here and C is up there. This means I want to find the length of this segment, or the distance from B to C, or the measure of that segment. How would I go about finding that? What tools do we have that allows us to find the measure of BC? Distance formula. Very good. We would use the distance formula because these are points, ordered pairs on a graph. We would use distance formula to find that length or distance. Very good. Okay. Real quick, talking about line segment, let's go back to line. So we have a point, string a bunch of points together, that's a line. Put a bunch of lines together, that's a plane. So a plane is represented by a flat surface that extends without end and has no thickness. Plane contains infinitely many lines. Okay, so kind of builds upon it. Again, it doesn't have thickness, just like the line, although we draw it, again, we keep going and see here. So the plane is a flat surface that goes on for forever and ever and ever and ever. So this could be a plane. I could have this as a plane. This is a plane. Infinite planes in space. I have the ceiling as a plane. The front wall as a plane. I could have this plane cutting through this plane. So again, just a flat surface. Alright, let's go ahead and head down to ray. And go down to angle at the bottom. So a ray is just part of a line that we have an endpoint and we have it going on for forever. Okay, so if line segment cuts off both ends, a ray basically cuts off one end. Our notation for a ray, we again use 2 letters, but we have to start off with the endpoint. So let's suppose I wanted to talk about this ray. What is my endpoint? What letter represents my endpoint? Good, B. So I'm going to start off with the letter B. And then the next letter that we label is what direction it's heading in. Now here, we actually have two letters we could choose from because C and A are both in the same direction. Totally up to you, it would be the same ray. I'm going to go and just say ray, B, A. Why not? To indicate it's ray, we draw a little ray over time. Now notice I don't change the order of my letters and the orientation of my arrow to match our picture, because here it's a nice horizontal one, but if I have something like this, where this is, let's say, Z and X, I'm not going to say, I'm not going to draw my picture then to be like this. Okay, so we always write it left to right, where our first letter is going to be the endpoint, and the second letter is the direction. So I don't want to see arrows going to the left. All right, so that's ray, B, A. Now, what if I had ray, A, B? Is that the same ray? Why not?
Because it's going the other direction.
Yeah, we have a different starting point, and we're going a different direction. Ray A, B would be from here, like that. Okay, so it doesn't matter what order you go with the ray. Now, can I measure a ray? No. Again, it goes on forever in one direction, so this has no measure. Now, what do you have when you put two rays together with the same endpoint? What do we call that? An angle! All right, go down to the very bottom of your page. An angle, two rays with the same endpoint. Now, an angle does have measure. We can take out that protractor and measure it. So an angle does have measure, so we do have two notations, one to talk about the angle, one to talk about the measure. When we talk about an angle, well, we have to have three letters to note our angle. We need to have the vertex labeled, and then a letter on each of our rays. I'm just going to call this ABC. So the notation we use is we literally just draw a little angle and then put ABC. The vertex has to be the middle letter. Now angle ABC is the same thing as angle CBA. Same angle, that vertex is the same. Sometimes we get to diagrams in which there are multiple angles happening. Some of our groups might have 12 different angles in it, and it's pretty tedious to have to write 3 letters for every single one. So sometimes our pictures will go ahead and label it with a number. So we could also just call this angle 1. Okay. So it's super nice when they give us that number. If there's a number, you have to use the 3 letters. Particularly when we get to diagrams like this. So sometimes we might have, let me just draw one off the, I'm thinking of a particular one that we do like this. And let's say this is C, this is A, this is B, D, E. Every year I have students that say angle C, but if we look, there's a point here, there are 4 different angles that are happening there. Now, if I said angle B, I know exactly what angle I'm talking about. There's only one angle there. So if it happens to be the only angle, we can use just the 1 letter. But when there are multiple angles happening, you have to use those 3 letters. Okay? So this would be an example where I'd have to say angle DCE to represent this angle. Okay. So that's when we're talking about the picture. But let's suppose we want to talk about the measure of the angle. Okay. So the measure of the angle, when we talk about the measure, I'm just going to write it in that it does have measure. So as measure. And our notation for that is simply that we put a little m in front. So the measure of angle ABC. So that means that we're talking about the measure of it rather than the picture itself. Questions so far? Nothing too earth-shattering, right? All right, I want to go ahead and continue along our thinking with our rays. So 2 rays together is an angle. Opposite rays. Who would like to say what they think opposite rays are? Just my signature. Vinny.
2 different endpoints and they're going different directions.
I like that, but we actually want the same endpoint. So we want the same endpoint, but they go in opposite directions. So we can see that pretty much makes a line, right? So two rays with the same endpoint that go in opposite directions. And they truly have to be opposite and that it forms a line. Okay. Now I want to build upon that and go to linear pair, but I feel we need to define a couple of things first before we do that. So I'm going to go ahead and hop down to our collinear points and our coplanar figures. Does anyone know what it means to be collinear? Let me see if I can get you guys there. So I can say that A, B, and C are collinear. I don't know, what do you guys think of that?
Points on the same line.
Yeah, they lay on the same line. So you can kind of see collinear has that word line in there. So collinear points lie on the same line. Any idea what coplanar figures are?
Figures on the same line.
Figures on the same line. Okay. So points on the same line. Figures on the same line. So collinear points are on the same line. Coplanar figures are on the same plane. So if I were to use my smartboard here as a plane, I could say that all these lines here are coplanar because they're all on the same plane. All right. And then I think I actually want us to flip to the back side. That's tiny. Yes. Adjacent angles. Does anyone know what it means to be adjacent?
Next to.
Yeah, the next to each other. So they actually share a ray. So our adjacent angles are angles that are next to each other and like smushed up against each other, so one of their sides is shared. All right, let me make sure I give you the true mathematical definition for it. So two coplanar angles. You'll see me use this notation to represent angles quite a bit. Little angle apostrophe s. Two coplanar angles that share a vertex and a side. Vertex and a side. Awesome. Let's go and flip back over to our linear pairs. We need to make sure we know what adjacent was before we did linear pairs. So key thing with linear pairs, so a linear pair, let me go ahead and draw an example for you. We have an angle, and we're going to have another angle that's adjacent to it, so they're going to share a side. So let's have it share this side. And the other chunk of the angle has to be an opposite ray. What do you notice about these two angles? Yeah, they form that line, they're supplementary, right? So now, supplementary is not in our definition, but it's important you make that connection for linear pairs and supplementary. We'll talk about that more later. But a linear pair is essentially two adjacent angles whose non-common side, so the side that they don't share, forms opposite rays. So basically makes that line. Okay, so adjacent angles. Adjacent angles. Whose non-common sides. Form opposite rays. And again, that non-common side is just saying the side that's not shared. So the other rays of the angles have to be opposite rays. And since it's a linear pair, that means two, so we're talking about two angles that do that. And as Keegan noted, we do see that they are supplementary. Okay. Let's see, where shall we go next? Let's talk about parallel, skew, and perpendicular. Ideally, you know what parallel and perpendicular are. Who can share with us what parallel lines are? Go ahead. Good. Two lines that never intersect. Now we're going to go a little more technical with geometry. We want to say coplanar lines, so they're in the same plane and they don't intersect, right? So coplanar lines that do not intersect. Now let's contrast that to our perpendicular lines. How is that different than parallel lines? Caleb.
Perpendicular lines that intersect.
Good. They intersect, and even more specifically, they form right angles. Good. So the definition is particular in that it says they form right angles rather than 90 degrees. We have to make the connection that the definition right angle means it is 90 degrees. Seems technical, but when we get to our proofs, it's really important to know that distinction there. All right, so perpendicular lines, I'm going to give you again the proper mathematical definition here. Lines that intersect. Again, they're going to be coplanar. So coplanar lines that intersect. I'm just going to put lines that intersect. If they intersect, they have to be coplanar. And form right angles. So if they're intersected, then they have to be on the same plane. Or they have to be coplanar. Coplanar means that one plane can contain both. Alright. Let's talk about skew lines. Has anyone heard of skew lines before? Awesome. Alright, so skew lines do not intersect. And they are on different planes. So parallel lines do not intersect, but they're on the same plane. Skew lines do not intersect, but they are on different planes. Okay? So, for example, say I got this line here, and then we take a journey back here to this line. Oh, my orange is not showing up as well on the outside. We've got that line there. Different planes, right? There's the plane at the front of the room and the back of the room. But also notice that I made sure my lines were in different directions. I have a vertical line here, kind of a slanted line there. If I were to extend this forever, never, will they ever touch each other? No, they can't wrap around in our plane geometry, plane flat surface geometry, they can't wrap around to touch each other. Now, the reason why it's important that they're in different directions is because if I put them in the same directions, I'm going to keep that vertical one there. Here. And like, well, hey, they're on different planes, right? So this is going to go up for forever, that's going to go forever, they won't intersect. But they are coplanar because there is a plane that stays flat, doesn't curve in the way, that intersects with them, okay? So that's why we need to ensure they're in different directions, because that will ensure that they're not coplanar. And we also, again, in our Euclidean geometry, our plane cannot go from here and then twist around and go vertical out there. So the different directions, different planes helps ensure that they are skew lines. Okay, so skew lines. So the definition is that they're non-coplanar lines that do not intersect. Let's write that out, but I then want to put different planes, different directions, because that's how I think of it. I think it's a little easier to think of it that way. So we've got non-coplanar lines that do not intersect. And so what that means is different planes and different directions. different planes in different directions. If you've got them on different planes and they're on different directions, then you're guaranteed to be seated. Alright, if they're on the same plane in different directions, then that's just a normal set of intersecting lines. Skew has to go to different planes. Okay. Questions with that? Alright. I've been talking too much. I want you guys to talk. So we're going to pause here. Go ahead and flip it over to the back side. I trust that you guys can define acute, obtuse, right, and straight angle. So I want you to go ahead with your shoulder partner once again, just together, go ahead and write out your definition for each of those.
I think my angle is 90 degrees. Or straight angle is 180. Acute.
And like actually go ahead and write it out. Yeah. Yeah, certainly. Eventually, you'll get an agenda, and that's what we're doing.
2 weeks, right?
Yeah, it's still going to be a while. So in the meantime, a post-it note will suffice. You're welcome. Not very close. So when you come out of the main entrance of the school, like door 8, and head towards the football field, there's it looks like a curved construction, so it says at All right, I'm throwing up the definitions for these, so you can just double check. What's a straight angle? An angle whose measure is what? Yeah, 180, so it makes that not 90. 180, so it makes that, it looks like that line. Now, the reason why I've left obtuse not filled in yet is because we want to be a little more technical with it. All right. Does anyone want to volunteer what they said for obtuse angle? Go ahead, Nesta. Very good. I'm glad you had the upper buffer. So an angle whose measure is more than 90, but less than 180. Very good. So where did that question come from? Yes, so we do have angles that are larger than that. So you'll deal with that once you get to pre-calc, and we go into this classification of terminal and coterminal angles. So basically 270 would be, so it's 3/4 of the way around the unit circle. So it's the same thing as 90 degrees in the other direction. Same thing as like negative 90 degrees. So in our geometry world, we're going to stick between 0 and 180. So obtuse is defined then as the larger one than between 90 and 180. But you're right, angles do go bigger. They wrap around more to make a circle. All right. Any questions with our angles? Okay, so let's talk about, you guys already know complementary and supplementary, right? Okay, quickly with your shorter partner, also do those two. What are complementary angles and supplementary angles?
It's a linear pair that is
All right, so two angles for complementary, whose measures add up to what? 90, yeah, for complementary 90. Now I heard some good vocabulary out there. I heard linear pairs. Do complementary angles need to be adjacent? Do they need to share a side? Give me thumbs up if you think yes, thumbs down if you think no. Do complementary angles have to share a side? The answer is actually no. So we just need two angles whose measure adds up to be 90. They don't have to actually share a side. No, most of the time when we talk about them and draw pictures of them, we have them share a side, right? But they don't actually have to share a side. So I want to make sure we make that distinction. So two angles whose measures add up to be 90. And then same idea for our supplementary, right? But what's different for supplementary? Yeah, they add up to be 180. And again, same thing, they don't have to share a side. So that's a big difference between supplementary and linear pair, is that linear pair has to share that side and make that 180. Supplementary, they don't have to. Okay, so you'll actually have some questions about that on your homework, or linear pair, supplementary, linear pair is kind of like the is a square, rectangle, square type thing. Okay. So that brings us to, in the angle world, vertical angles and angle bisector. All right, so vertical angles, this is a very common thing we see the whole year throughout geometry. And basically what vertical angles are, I'm going to draw you a picture of it and then we'll define it. So we get a nice beautiful S made up of lines. I have angle 1 and angle 2. Angle 1 and angle 2 are vertical angles. Some key things with this, it has to make that perfect X, which mathematically speaking means that the rays are opposite rays, right? If they're not opposite rays, like let's say I have this, okay, let's go with one opposite and one not. Those would not be vertical angles because it's not opposite rays, okay? So that perfect X comes from the fact that they have opposite rays. And then they are actually the opposite. Now in this diagram here, I labeled angles 1 and 2 as vertical angles. Let's throw in angles 3 and 4. Would 3 and 4 be vertical angles? Yeah, again, their sides form opposite rays. So vertical angles are simply two angles whose sides form opposite rays. All right, what do you guys think an angle bisector is? What do you mean to bisect something? Yeah, and even more importantly, split into two congruent parts. Good. So when we bisect something, it cuts it in half, basically. So an angle bisector is what's going to cut the angle into two congruent halves. Now there are multiple things that can cut into two congruent halves. Let me make sure I give you the right list here. A segment, a line, and a ray. Alright, so an angle bisector is a segment, a line, or a ray that cuts the angle into two congruent halves. We're going to talk about what that means, congruent. And the symbol that I use for congruent looks like this. And so it's a squiggle with equals underneath. You don't need the parentheses, I'm just saying in parentheses, that's what that means. So the two congruent. Congruent is a big thing in geometry. Many, many things come from that. Okay, what does it mean to be congruent? Thoughts? What does it mean to be congruent? Go ahead. Yeah, so it's equal measure. When we get into our figures, they're same shape, same size. We talk about in terms of angle. Each half of the angle would be the same measure. Okay, so congruent means it has the same measure. So when you cut it into two congruent halves, then each half is the same. Good. So let's go talk about congruent versus measure. All right, so congruent versus measure. Congruent is this symbol here, right? And this should actually say congruent versus equal. Scribble that out. It should say congruent versus equal. Oops. Okay, we all know what an equal sign is. So when we're talking about congruent, we're saying that shapes are congruent or figures are congruent. So we're talking about figures are congruent. When we say equal, we're talking about measures are equal. Measures are equal. So that could be the distance or the length of the segment or the measure of the angle. So for example, I would say that segment AB is congruent to segment CD. Notice that if we're talking about figures, that would be the segment notation with congruent. But if I want to say then what that means is that the measure of segment AB is equal to the measure of segment CD, which means that the lengths are the same, which is true. They're both true, but if you know one, you know the other. But the notation is what I'm trying to point out here. Segment are congruent, measures are equal. Same thing with angles, we would use angle ABC. Over here, we would say measure of angle ABC. All right, let's go talk about, real quick, postulates versus theorems. So geometry is a mathematician, Euclid, many years ago. Geometry was always in place, the rules of geometry, the statements of geometry were always true, but he's one of the main people that kind of discovered it and put it together in this format for us. So we have a series of statements that hold true in geometry. And our very beginning foundational statements we call postulates or axioms. So this is a statement that we accept as true, but it's so basic that we can't prove it. For example, if I have 2 points, how many lines can I draw through those 2 points? 1. We all agree it's 1, right? But that's one of our beginning postulates. We believe it's true, we accept it to be true, but it's kind of impossible to prove it's true because that's our starting point. Kind of like trying to define the word the. The is a single thing. What single thing mean? One. What does one mean? Single-minded. So you kind of find yourself going in circles. Now a theorem is where we can take statements we know to be true to prove other statements to be true. So a theorem is a statement that is proven true. A postulate is a statement we accept as true but cannot be proved. So super basic, we accept it as true but we can't prove it. Theorem, we can prove that. Okay, so for your part of your homework, you will have to fill out the segment addition, angle addition, postulate. I think I left you with the segment bisector up here and perpendicular bisector. So remember, your homework is to do lesson 2 homework, which is coming your way, and then fill in those remaining things. Now, our quiz next class is focusing on the summer assignment. You still need to do this homework because we'll continue talking about this next class. But the quiz is specifically over our algebra summer assignment. And then just a reminder, if you haven't filled out those 2 forms on the blackboard, make sure you get those done preferably before next class. everyone that did not get a copy of the homework? Okay. So lesson 2 homework, there is a little bit of facting. Just keep making you practice that for your quiz over summertime. Again, this geometry vocab will not be on the quiz, but it's still important for you to know because we'll keep talking about that.